Let's talk about a huge mystery in science. Why do so many really promising, really smart ideas just seem to disappear when they're put to the test in a study? Well, the answer might just be hiding in a paper from all the way back in 1998, one that totally changed how we should look for the truth. Let's get into it.
You see this happen all the time. A researcher has a brilliant idea, they run a big experiment, and they find nothing, a big fat null result. So does that mean their whole theory was wrong from the start? Or, is there something else going on here?
And this isn't some rare thing. It's a super common story, especially in fields that are trying to figure out messy things like human behavior. Researchers would come up with these hypotheses that made perfect sense on paper, but when they looked at the data, poof, the effect was gone. It was like promising ideas were just constantly hitting a brick wall. So you're left with two possibilities. The first one's pretty simple. Hey, maybe the theory was just wrong. The effect you were looking for isn't actually there. But the second one, that's where it gets interesting. What if the effect is real, but your study was like a blurry camera? It just didn't have the power to get a clear picture. To really get why a study might not be strong enough, we've got to introduce this other character that loves to complicate things. Think of it like a third wheel that shows up and just changes the entire dynamic of a relationship. This is the moderator variable. So, what the heck is a moderator? Well, it's a total game changer. Let's say you're studying how X affects Y. A moderator, let's call it Z, can just swoop in and change everything. It can make that relationship stronger or weaker, or even make it go in the complete opposite direction. Here's a super simple way to think about it. We all know coffee makes you more alert, right? Well, how much sleep you got last night is a huge moderator. If you got a solid 8 hours, that coffee gives you a nice little boost. But if you pulled an all-nighter, that same cup of coffee is going to have a much bigger effect. The sleep, the moderator, totally changed the game. Okay, don't let the math on this slide freak you out. Seriously, ignore all the symbols. The only thing you need to see is that last little bit, the interaction term. That's the fancy way statisticians capture how two variables work together to create an effect. And finding these hidden relationships, well, that's where it gets really, really tricky. So these moderator effects are kind of sneaky, and they're incredibly hard to spot. And the reason why they're so hard to spot is the real villain behind all those failed studies. It's a concept called statistical power. So, statistical power is basically the probability that your study will actually find an effect if that effect is real. The best analogy is a telescope, right? If you're looking for a tiny distant planet, but you're using a cheap, low-powered telescope, you're just going to miss it. And you'll walk away saying, nope, nothing's there, even though you were pointed right at it. Your equipment just wasn't good enough. So what's a good amount of power? Well, the gold standard in science is 80%. That means you've got a really solid 80% chance of finding the thing you're looking for if it's really there. Now, I want you to burn that number into your brain, 80%, because what this paper uncovered is absolutely shocking. This right here is table 1 from the paper, and it really gets to the heart of the problem. The researchers basically simulated what typical studies looked like at the time to figure out what their actual statistical power was. And the results were a massive wake-up call for the entire scientific community. Remember that 80% gold standard we just talked about? Well, in one very common research scenario, the power was just 17%. That means there was an 83% chance of failure, baked right into the study's design from the very beginning. In another common setup, it dropped even lower, to just 12%. And in some cases, it was a truly heartbreaking 9%. It's just, wow, these studies weren't failing because the ideas behind them were wrong. They were failing because they were designed with so little power, they were pretty much doomed from the start. So, if the power was that low, the next obvious question is, why? I mean, what was sucking all the energy out of these studies? Well, the paper pointed to a few key culprits. So here are the main power drains. Some of these are pretty intuitive, right? Like having a really small sample size. But others are a little more technical, like having uneven groups or only looking at a really narrow slice of your data, which can totally hide the bigger picture. And just look at how devastating one of these factors can be. Under perfect conditions, this study has 82% power. It's great, it hits that gold standard. But if you introduce a really common data problem called range restriction, the power just collapses to 19%. Nothing else changed. Just one single flaw completely crippled the study. But here's the best part. The authors of this paper didn't just point out this giant problem and walk away. They actually built a solution. They built a tool to help researchers plan for success before they even started their work. Their solution was this computer program that could run a power analysis. It let researchers kind of simulate their study ahead of time, plugging in their best guesses to see if their plan even had a chance. It was basically a pre-flight check for doing science.
And I just have to share this quote with you because it is the most 1998 thing ever. How did you get your hands on this cutting-edge software? You didn't download it. No, the paper literally tells you to mail a blank floppy disk and a self-addressed stamped envelope to the professor. It's a perfect little time capsule, but the idea behind the tool is as important today as it ever was.
And the process was brilliantly simple. A researcher would just punch in their study's details, the program would spit out a power estimate, and then they can make a smart choice. If the program says, you've only got a 12% chance of success, you know you need to fix your design before you waste years and tons of money on a project that's destined to fail. Now, you might be thinking, okay, that's a cool history lesson about floppy disks, but the core message of this paper is probably more important right now than it was back in 1998. And this is the big idea, the main takeaway. When you see a headline that says, a study found no link between two things, it doesn't automatically mean a link doesn't exist. It might just be an absence of proof, not proof of absence. Why? Because the study just wasn't powerful enough to find it. So I'll leave you with this. The next time you see a study that claims it found nothing, I want you to remember that blurry telescope. And then ask yourself, was the idea really wrong? Or was the study just not powerful enough to see the truth? It's a question that completely changes how you read the news and how you think about science itself.